Okay, let's get started. We were talking about projection theorem in the previous class. And I had promised that I'll give you a list of a bunch of projections so that it'll be handy when you use it next time. So the projection is I should say argmin here. X in capital X, and today we will study box set. So X equals to, I had given this already in the previous class, but I'll give it again today. Then sphere, and then so these are the three sort of sets where projection is a very simple operation. If you have a sphere which is centered away from the origin, then in that case you can also translate the axis and get the projection. We'll not talk about it, but those are the three sets on which projection is very easy to do. So in the case 1, the ith element of the projection is AI if Zi is less than equals to AI, Bi if Zi is greater than equal to Bi, and Zi if Zi lies between AI and Bi. This was what we did in the previous class. The second projection that was easy to do Z if norm of is less than equals to R square, and Z over norm of Z if greater than R. And in the third case, we'll define lambda, which is minus A transpose inverse AZ yeah. I'll draw a picture as well. This is my Z plus That's kind of sort of the picture you want to have in the head when you're thinking about projection. Okay, so projection theorem, what does it say? It says that there is a unique point on the set, within the set X, which is a projection of Z onto that point, and the other argument is that if you pick any other point in the set and you look at this angle, that angle always has to be greater than 90 degrees. So as you can see in all these three examples, that's what is happening in these three cases. And also the other thing to notice is how easy or difficult is it to do the projection. So very easy to do projection, very easy to do projection. Is this easy or difficult to do projection? Yeah, so if A is a very large matrix, then of course it's difficult to do the projection. If A is a small matrix, then it's easy to do the projection. So it depends on how many rows you have in the A matrix, because this is a M cross M matrix where M is equal to the number of rows of A. So if A has 100, 200, 300 rows, it's completely fine. If A has 1,000,000 rows, then it becomes a problem. Then you can't do projection. The other point I wanted to make is, if you have a set which is of this type, the projection is extremely difficult. Okay, so if you have a set of this type, do not use any method that uses projection, because projection onto this particular set is difficult, in the sense that every time you want to do a projection, you will have to solve a very complex quadratic programming problem. And because in the case of gradient descent methods, you have to do the projection at every time step, so then you have to solve a quadratic optimization problem at every time step, which makes things very complicated. Okay, so in order to solve this problem, you will have to solve this problem again and again at every point of time, and it could be complex, it can be easy, depending on how complicated the space is and how complicated these matrices are. So just to keep in mind, it's not like it's not doable. If you're solving a simple problem, it's doable. If you're solving a complex problem, which is what I assume most of you will be solving, it becomes difficult. Sometimes, when I'm saying complex, it also means that you might have hardware limitations. If you're using servers to solve this problem, it's probably easier. But many a times, I know, like a lot of people, a lot of students go to automotive industry, and automotive industry is always computationally constrained, because they always use like the cheapest microprocessor to do all computation, and cheapest microprocessors may not be able to solve problems of this type in every iteration. They can solve it once in 100 milliseconds, and if you are happy with that, that's fine. But if you have to solve this kind of problem in the cheapest microprocessor every 200 times every 100 milliseconds, then of course that's not going to happen. So sometimes the complexity is not because the problem itself is complex, it could be because of the computational hardware you have available to solve the problem. In the case of building thermal management system, which is what's controlling all our air conditioning system within the building, you can't actually solve these problems because they are using maybe a programmable logic controller. So the hardware is actually going to be an if-else statement kind of hardware. And if it is an if-else statement hardware which cannot do computationally complex programming linear or complex quadratic programming problem, then again it's the hardware limitations will prevent you from solving this problem in the hardware itself. I got exposed to it a few years back when I went to OSU and said, let's try to optimize some thermal, like the thermal cost, like the thermal management cost of the building. And then after a lot of discussion, we realized that it's not possible because they are using PLCs, and PLCs cannot implement these complicated optimization algorithms. So my dreams of optimizing OSU's budget still remains a dream because of the hardware limitations. Okay, any question? Okay. So let's go back to our discussion about the conditional gradient method as well as gradient projection method. Conditional gradient method means that my x bar k is argmin gradient fxk transpose x minus xk, where x is in capital X, and then I want to take the update this is the way to update. So we studied that in the previous class, and then the gradient projection algorithm is in both these algorithms, what's the common feature? The common feature is, first I want to find an intermediate point x bar k, which is within the set itself. It lies in the set capital X. Okay, but the way to find this intermediate point x bar k is different in the conditional gradient and gradient projection method. In the conditional gradient method, we expect that this linear programming problem will be easy to solve on the convex set. In the other case, in the gradient projection algorithm, we are assuming that doing this projection will be easy onto that convex set. And then what we will do is, we have this convex set. I have found this, I am standing at xk, I have found this x bar k, and I am just going to take a step in this direction. This is my xk plus 1. Okay, that's the idea. So I'm standing at xk, I figure out x bar k, which is an intermediate point. It could be within the set, it could be outside the set. We don't know. It depends on the iteration number and all that stuff, like the gradient of the function and so on. It could be outside, it could be inside. So I've just drawn one x bar k, and then I'm going to take a small step in the direction of x bar k, standing at xk. So I'm going to move in that direction. This is my xk plus 1. Now we need to figure out two parameters that we need to pick at every point of time. One is alpha k, and in the case of gradient projection, we also need to figure out what sk is. So that's what we are going to be talking about today. Okay, how to pick alpha k and how to pick sk. So generally speaking, alpha k is not going to be very different than what we have studied earlier. The only difference is going to be that alpha k now needs to be between 0 and 1, right? Because if you pick alpha k greater than 1, you might just overshoot, you might just go outside the set. So we need to pick alpha k somewhat more judiciously now in comparison to what it was for the unconstrained optimization problem. So in the unconstrained, we didn't really care if alpha k was large number or small number, but now we do care and we want it to be between 0 and 1. Okay, so what are the ways to find alpha k? Any questions so far before I erase? Okay, so alpha k limited minimization alpha in 0, 1. This is my dk. Armio rule, so this is limited minimization. Yeah, beta between 0 to 1, sigma greater than 0. And we want f of xk minus f of xk plus beta raised to m dk to be greater than equal to sigma and there is a negative sign. Were all of you successful in implementing Armijo's rule? Okay, so now you have a hang of what Armijo's rule is trying to do, and then the constant step size. Alpha k equals to 1. Okay, so these are the three methods. I mean, you can make up other methods also, but at least it gives you a starting point to figure out what alpha k you need to pick, and then you can iterate over it. For a specific problem which alpha will work, you can pick how you want to figure out the value of alpha at every iteration.
In the second, we will have alpha k equal beta m.
Right, beta raised to m. Beta raised to mk. Okay, so that alpha is used here and here. Yes?
I was going to ask if mk, does it specifically have to be an integer?
Not really.
Because if the gradient is like really, really tiny or really, really large,
Right.
wouldn't you want to choose something that scales your beta appropriately? Because otherwise it would just always select.
See, the more complicated the rule you make, the more complicated the code becomes.
Yeah.
So the question is to what level of complication you want to go to.
Okay.
So anything that you can do with non-integer mk, you can probably do something similar with an integer mk. So for instance, you might want to multiply it by, well, I am already using s, so I probably have to use something else here. What should I use? S0 bar or something like that. So you can pick something, some other multiplier here rather than just taking non-integer values of mk. Also, integer values of mk is easier to write in, I don't know, all kinds of programming languages, because you can put a while loop and then you can keep running m equals to m plus 1 and then break the rule if this condition is satisfied. So just everything is easier with just keeping it integer values. Yes?
How is it possible that x of k plus 1 will go outside the complex number?
It's only possible if you pick alpha k greater than 1. So, okay, so important point to note here. This xk plus 1 equals to 1 minus alpha k xk plus alpha k x bar k. This is a point inside the set, this is a point inside the set, and you are picking a convex combination of these 2 points. So by nature of convex set, this point, it's actually going to be inside the set, as long as alpha k is between 0 and 1. If it is outside of 0 and 1, then of course you have a problem.
But that also requires convexity.
Convexity of the set, but not of the function. So this is optimization over convex set, right? So this is all convex set that we are talking about. One of the things that people tend to do in optimization, and something that those of you who will do research in optimization will do, is whenever you have a non-convex set, you try to convexify the set by some means. You can, if you have a non-convex set like this, let's say this is your set, then you try to figure out what is the largest convex set within the non-convex set over which you can optimize. The other option could be you find the largest convex set which is encompassing the non-convex set, and then you try, once you find out the solution, then you try to find out whether that solution lies within the non-convex set or it's outside the non-convex set. So there are a lot of those hacky ways of doing optimization when you are doing optimization over a non-convex set by trying to solve a simpler problem, which is optimization over a convex set. Okay, so some things that you need to keep in mind if you're going to do research in optimization.
What if it wants to converge in that region that's outside of the convex set?
You have a outer approximation and inner approximation of the convex set, of the non-convex set, and then you try to, I don't know, like there's a lot of hacky ways of doing optimization over non-convex set. It depends on, sometimes when you have a non-convexity in the constraints, you try to put that non-convexity as part of the objective function rather than keeping it in the constraint. So a lot of those hacky things are done. So for instance, I don't know if you're aware of this. I'll give you an example because it makes things a bit more concrete. So I want to minimize some function of x such that the zero norm of x is less than equal to r. Anybody knows what the zero norm of x is? Number of non-zero elements in x. Okay, so if x equals to 1, 0, 0.01, then the zero norm of x is 2 because there are 2 non-zero elements in x itself. So sometimes in some situations you have problems of this type where you want to minimize the function over a set where the number of non-zero elements is less than equal to r. Okay, so now the question is, how do you solve this problem? This is optimization over a non-convex set. So anyone knows what this set looks like? Okay. So let's say x is 2-dimensional. So this is my x1 and this is my x2. And my constraint is x0 equals to 1. That's my constraint. Then what all points are feasible? So remember that origin is out of question because origin, the x0 is equal to 0, right? The 0th norm of x is equal to 0. So you have everything here, you have everything here, you have everything here, and you have everything here. That's my constraint set. So along the axis, except the origin. So this is a non-convex set, right? Because I can pick 2 points, and if I draw a line between the 2 points, that entire line is outside the set. So then you have this problem, you want to solve this problem. How do you solve it? It's not part of this course, but I'll still tell you how to solve this problem. you solve this particular problem. Where lambda is some multiplier, and then you multiply the norm of x0 with some lambda, and then you try to solve this. Now you have a unconstrained optimization with a non-convex function. But the problem is this function is still non-differentiable. How do you differentiate number of non-zero elements of x with respect to x, right? So this particular function becomes non-differentiable. So then you solve this problem. L1 norm of x. Okay? So instead of taking 0th norm of x, you take L1 norm of x and you kind of fiddle around with the value of lambda so that you get something which is kind of sort of falls within that level where norm of x0 is less than equal to r. So what typically happens is you pick a value of lambda, you solve this problem. If the number of elements is greater than r, then you increase the value of lambda, and then you resolve this problem, and then you see what norm of x, what the 0th norm of x is. If it is less than r, you're good. You can just pass it on as a solution. If you have a lot of points which are 0.001, 0.002, you just make it equal to 0, and then you try to. So a lot of hacky ways, there's no proof guarantee, there's no way, like a general way of solving that problem, but you can always come up with a hacky way of solving this problem, where you started with optimization over non-convex set. Then you said, okay, this is too hard to solve, so you converted it into optimization, unconstrained optimization, but with a different objective function. This is also very hard to solve, so you change the problem to optimization over a unconstrained set, but now the function is differentiable. Nice, and well, it's not differentiable at some point, but you don't care about those points. Okay, so you still are able to solve this problem.
What makes it unconstrained?
Because x is an Rn here.
And how was it constrained before?
This was the constraint before. This was the original constraint. So this is a non-convex constraint. You have a non-convex function over unconstrained set. Now you have maybe a convex function. If f is convex, then this is a convex function over an unconstrained set.
But we really use an approximation, not a.
Yeah, these are not equivalent problems. These are not equivalent. These are all approximations. So this is the problem you want to solve. What you do is you solve this problem and then apply some hack so that you get some solution which is better than a random guess that you might have. Okay? That's just the state of affairs in optimization. Any questions on that?
So then that would be making like an upper bound on the.
Correct. So that gives you an upper bound on like whatever solution you get here, as long as it satisfies this particular condition, after some hack, it gives you an upper bound on what is achievable.
And that's an upper bound on the other upper bound.
That's right, yeah.
Which is an upper bound on the actual solution.
Good. You are an expert on optimization now.
Is it possible to refine the answer we find with that method? And yeah, with that method we find an answer, right? Then we refine the answer.
See, the thing is you can do that, but the question is what's the problem statement? So if your problem statement allows you to refine the solution further, you can of course do that. The issue is that many a times you don't have any structure on the problem to be able to refine it further. Like no general ways of refining it further. Okay. Any other question? Okay, now our goal is to figure out what value of Sk we can pick, how to pick Sk. So I have to erase this side. So Sk constant alpha k equals to limited minimization rule. Sk equals to constant alpha k from Armijos rule third one is Sk satisfies and the fifth one is a bit complicated. So I'll try to explain the fifth one. So here alpha k is equal to 1. Armijos rule along the projection arc. So what is this? Armijos rule along the projection arc. So let's draw a convex set. That's my pizza slice. That's a convex set. And my problem is I'm standing here at xk. And my gradient is I need to move this pizza slice a little bit down. So let me do that. So I'm standing at xk and this is my xk minus gradient fxk. Well, actually there is a problem. I need to pick the direction carefully. Okay, this is better. Maybe I need a bit more. This is my gradient of fxk. Now one thing you will notice is as I'm moving along this line, so I can be here, I can be here, I can be here, and I can be here. So this is my xk minus gradient fxk. This is xk minus beta gradient fxk. xk minus beta square gradient fxk. Now look at the projection of these points onto the set. You get something like this. And this is called the projection arc. So what we are doing is we are picking the value of beta, we are picking the value of sk in a way. So first we pick beta raised to 0, and then I get to this point, and then I project it here. Then I pick beta equals to 1, then I get to this point, I project it back onto the set, and so on and so forth. Okay, that's what I'm trying to do here. And what I'm testing is, let me call this value x bar k of S. So I'm testing fxk minus well, no. Okay, so I guess some people are still writing, so I'll wait for them to finish. No, there is no negative here, so that negative is absorbed here. So dk is supposed to be x bar k minus xk, so it's kind of absorbed here. So here is what we do. We pick a value of s, we project it, we look at the difference between the function value here and the function value here. If it is above a certain threshold, so this is f of xk minus f of x bar k s. If it is above a certain threshold, we accept that as a step size and pick that point as my x bar k. If not, then I pick a lower value of s, and then I look at the difference in the function values at these 2 points. If it is above a threshold, great. If it is below a threshold, below that threshold, then I pick this point, project it back, and so on. So you have to do multiple projection in this particular case. So you can see like the number of projections you have to do, and then the number of function evaluations you have to do in this case is quite high. Now if projection and function evaluations are complicated numbers, I mean complicated operation, then you don't want to use this particular method. You probably want to use this one, or you want to use this one. So just something to keep in mind, which is depending on the computational complexity, you may not want to use this approach, and you might want to use something which is simpler. So we need function evaluation and we need projection both. Two complex operations happening in the same method. Any questions so far? Yes.
I have two clarifications.
Yeah, definitely.
So in the gradient projection,
here.
The first equation looks something like a steepest descent method where you're going in the opposite
That's right.
direction of the gradient and then projecting it back to the
Correct.
convex set.
Correct.
And in the next equation, it looks like you're going in the direction of x.
That's right.
So if you're already in the convex set,
Uh-huh.
you have already also moved in the direction opposite to the gradient, why do you need to take an additional step in that direction?
So those are the alpha k equals to 1 case. You're not really doing anything beyond projection. So if alpha k equals to 1, then xk minus xk cancels out and you only have x bar k as your xk plus 1.
Okay. And
But you can pick alpha k non-zero as well, not equal to 1 as well, in which case you get something in between. It really depends on the function landscape, and we are talking about the most general situations here, so we don't quite know what the functional landscape is going to look like.
And in the first 3 points, is S just a random constant?
I mean some constant, some random constant, which would come from either tribal knowledge of your area, or it might come from your gut feeling on that particular day. Okay, or trial and error. Yeah.
The essence of the gradient projection, first step being take a step, the second step being projected back in. Or am I thinking?
Well, in this case, the way I'm saying is that the first step is you take a step and project it back. Like first step consists of 2 operations. One is taking the gradient descent step and then projecting it back onto the set.
And then the second step represents.
Just taking a step in the. So I picked, let's say this is the point, this is my x bar k. I'm going to take a small step of size alpha k in that particular direction.
Okay.
And whether I go all the way to here or whether I go like halfway here is dependent on what value of alpha k you pick. If alpha k equals to 1, then you're going all the way to x bar k. If alpha k equals to half, then you're going like midpoint, and then you can decide which one works well for your function and your use case.
Why would it not be advantageous to have alpha k just equal to 1?
That depends on how nonlinear the function is, like the number of nonlinearities within the function itself. So, like for instance, I was in the candidacy exam and the defense of a student who was tracking space debris in the space. So they used to get like the GPS location of the space debris and they needed to project it. Like 10 hours later, is it going to hit a satellite or not hit a satellite? Like that was their research problem. And I think the kind of functions he was seeing within his application was highly nonlinear. So it depends. I mean, it was not like he was not solving a constrained optimization problem, but I know like whatever optimization problem he was trying to solve, it had a functions which were very, very non-convex. Because you see, the issue in those particular problems are you have an estimate of the position, you have an estimate of the velocity, and then you have all the gravitational pull and the dynamics of that particular object and so on and so forth. So whatever function you get is, I don't know, a concoction of all kinds of nonlinearities you can think of.
So you don't want to just take the biggest step.
Yeah, you don't want to take just the biggest step if it is constrained in those cases because it may not work out in your favor.
Yeah, that makes sense.
Yeah. Any other question? Okay. So let's talk a little bit about Newton's method, or something which smells like a Newton's method, but for this class of problems. I'm trying to figure out what the name is. It had a specific name. Constrained Newton's method. If no further questions, I'm going to erase this side. So here my x bar k is argmin x in capital X x minus xk and then in the case of approximate Newton's method, you change this to some matrix Hk, which is an approximation of the second derivative.
The approximation is what makes it the constrained.
Mm-hmm. What happened?
The approximation of the Hessian is what makes it constrained for.
No, not really. This one is what makes it constraints.
Okay.
Okay, so now I have this. Remember, in the case of Newton's method, we were trying to figure out the descent direction by optimizing the second order Taylor term. So first order and the second order Taylor term. So you're using that combination in order to figure out the descent direction. So there is only two differences here. The first one is, instead of trying to optimize the second order term, you have this term in the denominator sk. Now if sk is equal to 1, then of course you have the exact approximation, Taylor series approximation up to the second order. However, sometimes you need to pick a value of sk which is greater than 1 or less than 1, depending on how nonlinear the function is and how much you want to trust on the second order term of this Newton's method. So you can pick something like sk to be equal to 4 or 5 if you don't think that this particular term is that important. And that way you will have something which is like you are weighing it down, you are weighing the effect of this particular term down, and you are trying to increase the effect of the gradient term and decreasing the effect of the second derivative term by picking a value of sk which is higher, right? So this term, so as sk goes to infinity, this term goes to 0. So you can just adjust the value of sk depending on how much you want to trust this particular term in comparison to that term. The second difference is that now we have the minimization. So in the case of Newton's method, the minimization was over the entire set, but now that the entire set is not available, I'm going to do this argmin over the constraint set itself, over the convex set itself. And that becomes a problem because now we are kind of saying, just like we were saying in the conditional gradient, that maybe linear programming is easier over the convex set. Now we are saying that maybe this solving this optimization problem, which is a quadratic optimization problem, maybe the quadratic optimization problem over the convex set is going to be easier to solve than actually solving for the entire function itself. So just something to keep in mind, which is whenever you want to use this method, you want to make sure that solving this quadratic optimization is not too difficult. Again, something not that obvious upfront, but once you start implementing the algorithm, you will understand that problems of this type need not necessarily be easy. Any question? No? Okay. So I think we looked at 3 specific methods so far for solving constraint optimization problem, optimization over a convex set. So one is conditional gradient, which solves a linear programming problem and then takes a step. Gradient projection method, which uses steepest descent and a projection method and then takes a step. And then constraint Newton's method, which figures out Sk x bar k by solving a constrained quadratic programming problem. There is a 4th method that I want to talk about, which is submanifold optimization method. And this will be the topic for the next class. No, manifold suboptimization method, not submanifold. Manifold suboptimization. And in this particular problem statement, the idea is I have a constraint set X, which is of the type Ax less than equal to B. That's my constraint set. Remember, I said that this kind of constraint set is very complicated. So there is a completely different method for solving problems over this kind of constraint set. So this problem is hard to solve with that constraint. This problem is hard to solve with that constraint. And this problem is comparatively easier to solve with that constraint. But this is the class of algorithms. I think it was designed probably 1940s, 30s, late 30s, early 1940s. This algorithm was derived for solving linear programming problem. They wanted to solve minimum C transpose X such that Ax less than equal to B, and then later on it was generalized for solving arbitrary nonlinear problem. Why was this problem important in late 1930s and early 1940s? Why was linear programming important? What was happening in the world at that time?
They were shooting at each other.
They were yeah, exactly. So it was World War II time, right? So World War II, we had to move a lot of people all over the place. We had to move a lot of stuff all over the place. It turns out that those problems were solved, or they wanted to solve it, figure out what the optimal way of deploying troops is and what the optimal way of moving rice grains from United States to, I don't know, some front on France or Germany or whatever. So they wanted to solve all that problem, and they were investing heavily in linear programming because they wanted to figure out what's the cheapest way of moving things around for running such a complex worldwide operations is going to be. So that led to the development of manifold suboptimization method, which is one of the first efficient method for solving problems of this type. And then we'll talk about it in the next class about how this algorithm works. So anyways, that's all I have for today. We'll meet again on Wednesday, right?